Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 3, Section 1, Chapter 4, Topic 6. Mapping heat transfer paths to series and parallel models in semiconductor packaging. Examples and insights. Introduction. Understanding heat transfer paths is essential in semiconductor packaging for effective thermal management. These paths dictate how heat flows within a package and ultimately affect device reliability and performance. By mapping heat transfer paths to series and parallel models, engineers can gain insights into the thermal behavior of semiconductor packages and optimize their designs accordingly. This overview illustrates examples of heat transfer paths in semiconductor packaging and demonstrates how they can be represented using series and parallel models. Example 1. Heat transfer in a basic semiconductor package. Consider a basic semiconductor package consisting of a silicon die mounted on a ceramic substrate, encapsulated within a plastic mold compound, and attached to a heatsink. The primary heat transfer paths in this package include conduction through the substrate, convection to the ambient environment, and radiation from the package surface. Series model representation. Conduction through substrate, represented as a series thermal resistance component, R sub. Conduction through mold compound, additional series thermal resistance component, R mold. Convection to ambient, another series thermal resistance component, R conv. Radiation from package surface, series thermal resistance component, rad. Parallel model representation. Conduction through substrate, one parallel path for heat flow. Conduction through mold compound, another parallel path. Convection to ambient, separate parallel path. Radiation from package surface, yet another parallel path. In this example, the series model represents each heat transfer mechanism as a sequential path, while the parallel model accounts for multiple paths through which heat can transfer concurrently. Example 2. Multi-chip module with multiple heat sources. Consider a multi-chip module, MCM, containing multiple semiconductor chips mounted on a common substrate, each generating heat during operation. The package includes thermal vias for heat dissipation and is cooled by forced air convection. Series model representation. Conduction through substrate, series thermal resistance component, R sub. Conduction through thermal vias, additional series thermal resistance component, R via. Convection to ambient, series thermal resistance component, R conv. Parallel model representation. Conduction through substrate, one parallel path for heat flow from each chip. Conduction through thermal vias, another parallel path. Convection to ambient, separate parallel path for each chip. In this example, the series model captures the sequential nature of heat transfer paths, while the parallel model accounts for the concurrent flow of heat from multiple chips through different paths. Example 3. Advanced packaging with integrated cooling solutions. Consider an advanced semiconductor package with integrated cooling solutions, such as microfluidic channels or thermoelectric coolers, TECs, for enhanced heat dissipation. The package includes multiple heat sources distributed across the substrate, and cooling solutions are strategically positioned to remove heat efficiently. Series model representation. Conduction through substrate, series thermal resistance component, R sub. Conduction through cooling channels, additional series thermal resistance component, R cool. Convection to ambient, series thermal resistance component, R conv. Parallel model representation. Conduction through substrate, one parallel path for heat flow from each chip. Conduction through cooling channels, separate parallel paths for each cooling solution. Convection to ambient, separate parallel path for each heat source. In this example, the series model captures the sequential flow of heat through different materials and structures, while the parallel model accounts for the distributed nature of heat sources and cooling solutions. Insights and considerations. Series model provides a simplified representation of heat transfer paths, suitable for initial thermal analysis and conceptual design. Parallel model offers a more detailed analysis of complex thermal behavior, enabling optimization of cooling strategies and heat dissipation pathways. Conclusion. Mapping heat transfer paths to series and parallel models provides valuable insights into the thermal behavior of semiconductor packages and facilitates the optimization of thermal management strategies. By understanding the characteristics of series and parallel models and applying them to real-world examples,
engineers can effectively design semiconductor packages with enhanced thermal performance, reliability, and efficiency. Thanks for watching.
Please like, share, and subscribe.